Hi everyone, my name is Donna Kern, and today I will be talking about a collaborative project between NREL and Slack on interface degradation in glass-glass photovoltaic modules. And when I say glass-glass, that refers to the module construction that includes a sheet of glass on both the front and rear sides of the module instead of using a more typical polymer backsheet on the rear side. So here's an outline of what I'll talk about today. There has been increasing interest in and deployment of glass-glass packaging, which has stemmed largely from growth of bifacial, long lifetime, and thin film technologies. For this reason, Dermat has started a glass-glass focus group, and I encourage you to contact me or Archana to take part in our meetings if you want to help define the roadmap to greater glass-glass durability and how Dermat can help researchers address these challenges. But with that being said, the second point I want to address is that glass-glass modules have been around for 20 years or more, so there's a lot that we can learn from history before we start to reinvent the wheel. To this end, our group has recently submitted an in-depth review article where we go over observed failures in older generation glass-glass modules, and then we talk about more recent trends in module materials and construction. In this review, we outline how accelerated stress testing procedures have to be modified to account for glass on both sides. For example, the influences of rear side UV exposure, power generation from the backside, new sources of sodium ions and PID tests, changes in mechanical strength, and so on. We then show various characterization methods that are particularly suited for understanding glass-glass laminates, from non-destructive imaging or power analysis to more destructive interface characterization, for example, with adhesion tests or microscopy. We also discuss system-level considerations like the components needed to handle higher currents when bifacial cells are used, as well as practical concerns in mounting and greater module weight. Then we finally go over some general trends like replacing EVA with other encapsulants like POE or even no encapsulant between the glass sheets, and how some changes like this can start to result in new generations of more durable module designs going forward. So keep an eye out for our review. So despite an extended history of older generation glass-glass modules, glass-glass packaging designs are significantly evolving, and it's important to run careful lab studies to make sure that we're choosing the best materials for durable modules. For this reason, I'll go through a subset of recent results in our Duramat glass-glass project, where we compare glass-glass versus glass clear backsheet mini modules. In this project, we combined accelerated stress testing and non-destructive spatially resolved characterization with more destructive analysis of mechanical strength and changes in chemical composition. From these studies, we show different degradation mechanisms between glass-glass and glass-clear backsheet, including effects of potential-induced degradation and moisture ingress. We concluded that glass-glass modules using POE as the encapsulant are more durable than those with EVA or backsheets. In parallel, I'll show just a few observations in field-weathered glass-glass and glass backsheet modules to help discuss things like the relative mechanical strength and operating temperatures in outdoor environments. So here's a flowchart of the project that I just described, where the first line indicates our test samples that undergo accelerated stress. And in this case, we run damp heat at no bias or at positive or negative 1000-volt system bias. Before and after the stress testing, we run current voltage curves and imaging using photoluminescence, electroluminescence, and dark lock-in thermography. For even more non-destructive characterization, we're now also doing spatially resolved external quantum efficiency measurements. And once all of the non-destructive testing is complete, then we core the areas of interest. So we're currently in the process of destructive interfacial characterization using XPS and Auger spectroscopy. In parallel, we're also running adhesion tests of coupon samples and some analysis of fielded modules. So the samples for accelerated stress testing consisted of glass-glass and glass-clear backsheet modules, each with either an EVA or a POE encapsulant. Here I'm showing a photo of the samples in damp heat under the different bias conditions, where the bias is applied between the cell and the module frame, and the frame is simulated by an edge of aluminum tape. Under accelerated stress, there are a few different possible impacts of the module construction on the degradation mechanism. The first obvious one is the impermeability of glass both to moisture ingress and to the out diffusion of encapsulant degradation products. The second factor is that glass supplies an extra source of sodium ions on the backside of the module. This could result in potential induced degradation by sodium migration to the backside of the cell under negative system bias, which wouldn't necessarily happen with a backsheet. Under positive bias damp heat, a different type of corrosive PID has been suggested to take place, where samples having rear side glass might be more susceptible. This corrosive mechanism could affect the metallization or the rear side stack, including the passivation and the anti-reflection layers. With that said, here are results for changes in IV metrics that we recorded both on the front side and the rear side of each mini module, including the 4 different module constructions that we made. Along the bottom of the chart, you'll see the 4 different stress tests listed for the measurements both for the front and the back side, including the control samples, damp heat under negative bias, damp heat under positive bias, and damp heat under zero bias. The first thing to note is that all samples with EVA encapsulant showed greater degradation than those with POE encapsulant, regardless of whether they were glass-glass or glass-clear backsheet. The most severe degradation was usually associated with damp heat under negative bias, which results in fill factor loss predominantly from shunting in the IV curve. Interestingly, for the glass-glass EVA samples, we also saw VOC loss under the negative bias damp heat in addition to that typical shunting mechanism. I'll show you this later in the imaging, but we attribute this additional VOC loss to a backside polarization effect that decreases the passivation quality. The only case where negative bias damp heat did not give the biggest power loss was for the glass-glass EVA module, specifically on the rear side. As you can see here, the glass-glass EVA sample had the greatest power loss under positive bias damp heat, and this was mostly associated with VOC and short circuit current losses with minimal change or even a slight improvement in the fill factor. Now we can get even more insight into the changes in IV metrics using non-destructive spatially resolved analyses. Here I'm showing just the negative bias and positive bias damp heat, since those are the conditions where we saw the most degradation. For each module, we recorded images of photoluminescence and electroluminescence, labeled here as PL and EL, as well as the dark lock-in thermography under forward and reverse bias conditions, labeled as DLIT plus and DLIT minus. In each sample type, there are 2 associated rows of images. The first row is the sample before stress, and the second row is the sample after stress. To go along with the imaging, I'm also showing the external quantum efficiency curves labeled here as EQE. The EQE before stress is a solid line, and after stress is a dotted line. The blue is measured on the front side of the module, and red is on the back side, and the same color coding goes for the IV curves. So now I'll zoom in to look at a couple of the most interesting comparisons. Here I'm showing the glass-glass EVA compared to the glass-clear backsheet EVA under negative bias damp heat. In both cases, we're seeing that shunting type change in the IV curves, which is that typical process of sodium ions diffusing from the glass to the cell under negative potential, causing those local shunts. Using the images, we can see some shunting in the DLIT minus image for the after stress scenario. There's lots of shunting around the cell perimeter for the glass-glass sample, and some more shunting in the cell interior for the glass-clear backsheet case. In addition to shunting, we also see series resistance effects, which is most obvious by comparing the PL and EL images. For the glass-glass sample, you see it in the upper corners, and for the glass-clear backsheet sample, you can see it along the bottom edge. In both cases, the series resistance manifests as areas being exceptionally bright in the PL while they remain very dark in the EL. Here's a zoomed-in view of PL images showing that series resistance effect that I'm talking about, and I'll just quickly mention a different method for really visualizing series resistance in these PERC cells. There are multiple ways to measure photoluminescence, including using either a full area diffuse illumination or illuminating with a scanning laser beam. For PERC cells in particular, we see the series resistance effects become really emphasized with the scanning laser method. And we also find that we can use the scanning laser method to visualize the backside PERC local contact pattern even when we're imaging from the front side of the cell. So I actually find it really interesting that neither of these resistance type effects, like the series resistance or the shunting, seem to show up significantly in the EQE curves. That's especially obvious for the glass clear backsheet sample. And I believe what this is telling us is that our EQE curves are dominated more by the semiconductor quality and the efficiency of light absorption rather than changes in the resistance parameters. In the glass-glass sample, we do see a drop in the EQE for the rear side after stress, and I'm attributing that to a rear side PID polarization effect, which also shows up in the PL and EL images as a dark splotch near the center of the cell. This PID polarization has been seen by others, and it is more specific to the glass-glass structure, where sodium ions diffuse toward the backside of the cell from the rear side glass. The positive ions then counteract the quality of field effect passivation from rear side layers like aluminum oxide. The other interesting degradation process that I'll note is the positive bias damp heat for the glass-glass EVA sample. In this case, we saw minimal resistive effects, and the degradation was mostly dominated by loss of the backside passivation and optical quality, which is shown by the severe loss in VOC and ISC. From the images, we see an overall loss of luminescence signal and increase in the heat dissipation, but the degradation is most severe as a halo around the module edges. Looking at the EQE, we see almost zero EQE for the backside at the short wavelengths that would be absorbed closer to the cell surface, and then increasing EQE as photons get absorbed more toward the bulk. This tells us that it's a problem with the backside recombination, and now we're just getting started with coring in microscopy to look into the possible corrosive process that could happen on the rear side. Now, before I wrap up, I'll just show you a parallel evaluation of fielded glass-glass modules. This is just a quick example of modules that were weathered outside for about 2 to 3 years at NREL, during which time they were all operating side by side and they all went through a severe hailstorm. The EL images show 3 glass-glass PERC modules starting from the left, which we compare with an aluminum BSF glass backsheet module on the farthest right. The imaging mostly shows uniform EL images that aren't too different from the control, aside from this large amount of cell cracking in the aluminum BSF module. So this is an important indication of the greater mechanical strength of glass-glass modules due to their symmetric and more rigid laminate compared to the glass backsheet module. In terms of the different processes for cell degradation, we see that the PERC modules tend to grade more in VOC, while VOC degradation is not typically the primary degradation process in the older generation modules like aluminum BSF. And you might have recently heard Dirk Jordan speaking about this type of VOC degradation at conferences, where this new type of degradation process seems to occur in higher efficiency modules like PERC and silicon heterojunction. We believe that the VOC degradation process that we observe may be associated with hydrogen redistribution in higher efficiency cells, which affects the cell's passivation quality. Here I'm showing depth profiles of the normalized hydrogen concentration using dynamic SIMS, where we compare a control, bifacial, and monofacial glass-glass PERC module. The results seem to suggest greater hydrogen diffusion for the bifacial glass-glass modules, especially on the back side of the cell. And this is all really preliminary, but it's an interesting question to consider whether this degradation process may be thermally activated and if factors like the cell bifaciality or the glass-glass packaging could lead to higher temperatures that accelerate this type of diffusion process. Just to recap, we're actively working on building up a roadmap toward greater durability of glass-glass modules. The first step towards this goal was an extensive review article to learn from history and what's been researched so far. We then ran lab tests to understand various factors of the module construction and how the degradation processes change under different stress environments. We found that EVA is generally not a good choice for glass-glass modules, and POE encapsulants can help to avoid many of these degradation pathways. We also showed different degradation pathways depending on the laminate construction, particularly how backside loss pathways change when you have a rear side glass sheet rather than a clear back sheet. And finally, it's obviously important to note that the module construction will have to be optimized depending on what stress conditions the module is expected to experience. In our studies, we highlighted the different impacts of PID, moisture ingress, and mechanical strength that vary between glass-glass and glass backsheet modules. So with that, thanks for listening to my presentation, and thank you to the various people who have helped with this project, along with the DOE and Duramat for funding. Please contact me or send me an email if you want to discuss further.